Okay, so time to start, to restart. So I have the pleasure, buongiorno, buongiorno, to leave the floor to our first speaker of the last session. So Professor Josef Pochodzalla, who is going to, so there is no slide. Okay, we have it.
You want to have it, okay.
Okay, so the title is the same, yes.
Yes, I left the title the same, the content is a little bit different.
Okay,
that's usual for me.
Measurement of hydrogen 6 ground state energy at MAMI. So, thank you. You
Okay,
have 35
good morning.
minutes plus 5.
The common feature of the last day after dinner is, of course, that people come late or not at all, but that's usual for conferences, so this is typically. Yes, first of all, I would like to thank the organizers for inviting me here to Brazil, the first time in Brazil, which is I enjoy very much. Also, the place here is great. What I must say, I'm a little bit an exotic in this meeting. I'm not in that community, which is not so bad, but even that, I'm not a theoretician, but I'm an experimentalist, so the penalty factor squared at least. Nevertheless, I hope I can convince you that we are doing interesting physics. Since this is a meeting, in the title of the meeting there is nuclei and stars, I have added a short section where I will tell you that there might be more than just a tetraneutron when it comes to neutral baryonic systems. This will be a very short tour through strangeness nuclear physics, where my heart is lying. And then I have to find the right button. Then I will come to the main topic of this talk, the hydrogen 6 and the experiment at MAMI. And I will show you what we have done. This is based on the recent PhysRev letter which we published with this measurement here of the hydrogen 6 mass. Let me start with a short tour through other possible, I stress possible, neutral systems, because we have only circumstantial evidence for that, not really clear proof. This is your playground here at the meeting. The nuclear landscape, conventional nuclei made of protons and neutrons. This is where we live in. However, we know that the world is not flat. We know that since 500 years before Christ and in the medieval, people ignored science somehow and said the earth is flat again. This was fashionable. But it's like today, yeah? We have to make sure that not the ignorance win, but science at some point, hopefully, again. So we know the world is round because we are here in Brazil. I made this arrow pointing downwards to the north part, so I was careful in that. So the motivation, or the reason why I think the Earth is round and not flat, is the following. There's one place where hyperons might be important, namely in a neutron star. And this was also in the title of this conference, star, or stars in general. But one of the most interesting things is, of course, what is a neutron star and what is in the inner of the neutron star. The argument is very simple. And you learned this in your first class of nuclear physics, that if you compress a Fermi gas, the chemical potential of the neutrons will rise with the density. And at some point, you have enough energy to convert. I have to watch out for my fingers here. You can convert the neutron into a hyperon. That is fairly easy. And the reason why this works is that the hyperons, that the time scale for the explosion of a star is large compared to the weak decay time of hyperons, which is of the order of 10 to the minus 10 seconds. And once these hyperons appear, they can no longer decay in the other direction because this is Pauli suppressed. And that is a long debate at the moment, and this very interesting. Do hyperons appear in neutron stars or not? So this I will not talk about because this would be a whole conference by itself. But I will take this just as granted for the moment. That is, this is an interesting question. And that is the reason why we study not only conventional nuclei, but we study so-called hypernuclei. And these hypernuclei usually contain a lambda hyperon, because this is the lightest hyperon which exists. It's, so to say, the heavy partner or the heavy sister of the neutron, because it's neutral. And usually these hypernuclei, which are shown here, these are the known hypernuclei. The nomenclature is such that you have here the number of baryons, including the lambda. You have the number, the hyperon, and then you have the number of protons here in the element. So hydrogen 4 lambda is a nucleus made out of 1 lambda, 2 neutrons, and 1 proton. And most, or some of them, decay via the weak interaction. That means like the lambda decays, the lambda hyperon decays into a pi minus. That should be a pi minus, so I think this is the wrong, but it doesn't matter. This is the presentation, but this has not been corrected yet. So it decays into a pi minus plus a proton. So this hypernucleus here, for example, decays into a pi minus and a helium-4 nucleus. And the pi minus can be detected. And the nice thing is, in these decays, these are monoenergetic pions. So a hypernucleus, the fingerprint of a hyperon is in the system of the hypernucleus, is a monoenergetic pion. So this is easy to identify, because each hypernucleus has a distinct pion energy given essentially by the masses of these nuclei. And you see what we have at the moment. We have roughly 20, 30 of these so-called single hypernuclei, where we have 1 hyperon in this system. There are also very neutron-rich ones, like the lambda 6 hydrogen. So this is a nucleus maybe interesting for the tetraneutron. It's 4 neutrons, 1 proton, and 1 lambda. But, and this is the main point I want to make here, there are also neutral systems. And the advantage of these neutral systems is, if they exist, that they are long-lived. That means they are stable compared to nuclear interactions. I mean, they decay weakly, so this is long compared to any hadronic interaction. So, N and lambda, this is the first one I pointed out. This was seen in an experiment at the GSI some time ago. Here it was published more than 10 years ago already. So this is the spectrum, the invariant mass spectrum, then reconstructed from this decay. N and lambda decays into pi minus plus tritium. And you see the background here given by that band, and you see the signal here in different conditions of the experimental apparatus. You see also the problem here is that the background has a width which is only marginally larger than the peak. The resolution in this experiment was not perfect, but it was the first experiment. You can now, of course, ask yourself, is that possible that such a beast will be produced? And for that, you usually in heavy ion reaction use statistical models, because they work quite well for normal fragments. They predict the production of fragments very well. And if you plug them into these models, such a state, it is indeed produced with a high percentage. So it's not an exotic nucleus if it is stable. Of course, and that is the problem, no theory really supports such a stable system. And that is the reason why new experiments were performed. There was one experiment in 2018 at JLab, which was a very nice experiment. They used a tritium target, so this is a one-shot experiment. Nobody will repeat ever this experiment with a tritium target, because this was a pain in the neck to operate that. And the outcome is, well, there might be something around the peak, and the statement in the paper is very cautious, of course. However, to make a definite identification, improved statistics are required. Unfortunately, as I said, the tritium target is no longer in operation and will probably no longer be in operation in future. There's another experiment which was done in 2022 at GSI, so the follow-up experiment at the GSI with an improved detector. The so-called VASA detector was used in this experiment. This is not yet fully analyzed. This is the spectrum they expect for this experiment. So it should have a better resolution and also much higher yield. And we are waiting now, of course, for the results coming out. I hope that not later than by the HYPE conference, which is the main conference for this field in October, that this result will be presented. So there may be something, it's interesting. Maybe more interesting is an even more exotic nucleus, namely the double hypernucleus lambda NN. And this is, of course, difficult to detect. And there's indirect evidence. There was a beautiful experiment 25 years ago, so good data don't age. It was 25 years ago. What they did in this experiment, they used at AGS in Brookhaven a K- beam and produced a K+. So this produced in the target nucleus a cascade minus. This is a doubly strange hyperon, baryon. It's negative, so it's then captured into the atomic orbit of another target nucleus, is cascading down to the nucleus and then captured by the nucleus, and it produces a double hypernucleus. In some cases, it may also produce a pair of two single hypernuclei, where the two strangeness units are distributed over two single hypernuclei. The point is, or the signature then of these doubled hypernuclei are these two monoenergetic pions from the sequential decay of such a double hypernucleus. So you observe two monoenergetic pions in coincidence together in this experiment with the K+ to detect the K cascade production. And this is what they observed here, this scatter plot here. They observed some bumps. They can be attributed partially to double hypernuclei. In most cases, these are indeed twin hypernuclei, so two single hypernuclei, which are not so interesting. But the problem is that they have yield down here in that area. And it is simply impossible, because of energetic regions, to describe this area by any known single or double hypernucleus. There's not enough energy to produce this bump here in that region with a conventional known double hypernucleus. And what we did then, or the suggestion, this was done very early by Avram Gal, the living Bible of hypernuclear physics in our field. He suggested already very early that could be the NN lambda lambda. That would explain that bump. And indeed, we plugged that into a statistical model, and you see here the result. It nicely explains this area in this region. So there is some, not direct proof that this system exists, but there is some circumstantial evidence that it might exist. Good. This is enough about hypernuclei. What you should take home from that is that we should consider the structure of conventional and strange nuclei together, because I have learned you have a lot of experience of normal nuclear structure, and I think that is very useful also for hypernuclear systems. Some of you, of course, work in the field. Hans, Emiko, haven't seen her, and others, they are working also in the field of hypernuclear physics, but I think that can be improved, that working. The caveat is, of course, in hypernuclear, our experimental information is limited. We certainly cannot do experiments, scattering experiments. That is not possible. And the reason for that, I think we need this cooperation somehow, because finally we want to understand these strange things like the neutron star. So now I come to the main part of my talk. I spent already too much on the previous one. Here, this is the main topic of this talk, the hydrogen-6 nucleus. This is the most, except for then hydrogen-7, which I will not talk about, this is the nucleus with the largest neutron-to-proton ratio known so far. And that's why it's interesting. It's also interesting, I should say, there's a recent experiment at the GSI where they measure the isospin partner here on the very proton-rich region. So also that's why I think it's interesting to know how these heavy hyper hydrogen nuclei behave and look like and whether they exist. Now, hydrogen 4, hydrogen 5, there seem to be some clear signal of them. They are observed. For the hydrogen 6 and hydrogen 7, this is very unclear. I will show the signals of the hydrogen 6 in a second. These are the signals of hydrogen 6. You see here the table, here the resonance energy with respect to the tritium NNN threshold. And this is was the first measurement. This bump here was attributed in this rather complicated exchange reaction to the hydrogen 6. They speculated about a few other states here. This was then followed up by the same group, more or less, with another target nucleus. And they observed that bump here, the broad bump here, which is again compatible or has been attributed to the ground state of hydrogen 6. This threshold here is at 0. And this is those data at reasonably small binding energy. And then later, 20 years later, experiments were performed with pions. This is these series of experiments. You see the background is rather large, the statistics is moderate, and they associated these bumps in the spectrum to several states in hydrogen 6. Whether one believes that or not, this is a different question. Then, most recent, there's an experiment which sounds complicated. I will show you this in a minute because that looks great. 4 events here, or 3 events actually are these, and you have a small peak with no background, but be careful. And this is the most recent measurement, now 22, where they couldn't see really a ground state here at low binding energy, and they could only give a upper limit for a lower limit for the mass, and for also the width is large if this is attributed here to the ground state. Now let me show you, because this is I meant for the theoreticians, for the young students, that they should really look into the experiment which produces the data they are dealing with. And that's the reason why I do that. This is a beautiful experiment. They used a helium-8 beam on a carbon target. They detected the triton as an indication of the decay of a hydrogen isotope, heavy hydrogen isotope, so this was the signal somehow, and they detected in this active target the nitrogen. They did not detect the atomic number of the nitrogen, just the element number. So they didn't know which isotope that is. And now they have measured roughly 20 events of that kind. And now they did an analysis assuming that this is hydrogen 15. In this case, the decaying nucleus here would be a hydrogen 5. And they converted that into the excitation energy scale, and then they attributed those events to hydrogen 5. There are other events here, obviously, which they cannot be hydrogen 5 then. And then they did the same game, assuming that this is nitrogen 14, then this part here has 3 neutrons, so it's then hydrogen 6, and these are those events. And these 3 events are shown here in that plot. And the rest of the events around here, they are ignored. And then they convert that, you unfold this with the resolution. Obviously, the peak is much broader than the resolution, and that's the peak they then extracted from this analysis. That's the way it is published. Now for the hydrogen 6, so assuming nitrogen 13, this is this peak. This looks more convincing because there's at least no background on the left-hand side in this spectrum. So, but I must say, as an experimentalist, whether one should believe such a narrow peak from the reconstruction, I do not know. Well, it depends. You have here the number of neutrons and protons, which are fixed. That means if this is a nitrogen 17, you have in total 1 proton and 4 neutrons here on that side. So this is then decaying a hydrogen 5 into tritium plus 2 neutrons. Yes, exactly. That's what I did. They made an analysis assuming certain nitrogen isotopes. So all these events, they are the same events. This is not an independent measurement. You make the analysis assuming a certain isotope of nitrogen has been detected here. We can discuss this later. This is an interesting story. Okay, now theoretically the situation is also unclear for the hydrogen 6. This is what we have. There are several shell model calculations with different resonance energies. So again, this is the resonance energy above tritium plus 3N. And you see this is scattering around from about 2 MeV up to 8 MeV or so. And here is a molecular dynamics calculation, recent one, 2004. And this is a calculation from the chairperson who is not here, I think. Emiko is not here. Oh, it's there. Emiko is there. Hey, hello. So this is her prediction. It's about 10 MeV for the ground state of hydrogen 6 in a cluster model. So what do we learn from that? Well, experimentally it's not clear, theoretically it's not clear, and it would be nice to do a different experiment. And we did a different experiment, avoiding, and this comes now to the question which certainly Carlos will tell, avoiding that the hydrogen 6 is part of the original nucleus. We have learned yesterday this is part of the tetraneutron, that these 4 neutrons are contained in one of these nuclei, which that means the tetraneutron may be just a reflection of some initial 4 neutrons in a target nucleus. This we do avoid in this experiment because we produce an additional neutron inside the target. So briefly about MAMI. MAMI is an electron accelerator. We have up to 1.5 GeV energy. We use in this experiment only the second but last stage of this combination of so-called microtrons with about 850 MeV electron energy, and we shoot them here into the A1 experimental hall. This experimental hall is shown here. We have there 3 big high-resolution spectrometers, which can be rotated around the target position here. And these are focusing spectrometers. That means they have extremely high momentum resolution. They have also here large acceptance, which is important for the experiment in the beam direction of about 5 centimeter. And what we do is very simple. We do a missing mass experiment, scatter the electron scattering on a lithium-7 target, and we detect the scattered electron, the proton, and the pi plus, and the missing mass is then the hydrogen 6. So in principle, it's very simple. And actually, I should say this is the second experiment where all 3 spectrometers were used in the triple coincidence over 40 years, something like this. The first experiment was done when I arrived at Mainz, but it was not successful. Okay, so now if you want to measure something like that, the scattered electron, proton, and the pi plus, you have to have some picture of the process, because otherwise you cannot make any prediction or tune your setup or whatever. Unfortunately, nobody can tell us this a cross-section for this process. This is simply not available. And then you have to make an educated guess. And here your fantasy comes into, and it could be completely wrong, what we thought about. What we said is, okay, we want to produce a pi minus. So what do you do in order to produce a pi minus by electron? You produce a delta. This is a large cross-section. So this helps. So that makes sure at the beginning you have at least a pi plus. So you have converted 1 proton into a neutron, already 1 proton away. And then you assume, because there is still 1 proton to be removed, you assumed that this neutron, which comes from the delta, scatters on the proton and ejects the proton more or less into the direction of the neutron. Because then the momentum of the neutron is reduced to the momentum of the proton. So it's a low momentum neutron which you then have. That means you have a high probability that this is captured into the hydrogen 6 nucleus. Okay, nobody could tell us the cross-section. Then we did my own Monte Carlo, Poorman's Monte Carlo, and some evaluations. This I can just do as an experimentalist, not more. And what came out that the expected rate is 1 event per day, which is not a lot. But nevertheless, if you measure 3 weeks, you have 20 events, and that would be okay. And it actually turned out, I make that point also later, this was confirmed. So somehow this mechanism which we indicated here may be indeed something close to reality, but there is no proof to that, of course. The missing mass resolution we expect for this experiment is about 1 MeV with our used lithium target. And then, of course, you have to define the kinematics. That means since these spectrometers are not for pi detectors, but they have limited acceptance, that means you have to determine what momentum you want to set for the spectrometers and what angle. And of course, this is guided by the process I have shown before. There's a nice calculator by the A1 collaboration where you can play around. Of course, the main point is you cannot move these detectors, these spectrometers everywhere because they cannot overlap, obviously. Unfortunately, this is not possible. So there are some mechanical limitations simply for the setup. But we found a solution which gives a low momentum transfer to the hydrogen 6. This is important. Otherwise, it would be very unlikely that you produce this nucleus. The lithium target, this is nice for those who are interested. This is now for those people who want to work with a lithium target. Actually, we did it differently. We did not shoot on a normal conventional target like we did for 40 years at A1, but we decided, because we needed luminosity and we did want to limit the temperature of the lithium target, because lithium has a very low melting point, so it's not easy to handle. We shoot along the target, through the target with the electron beam. And that was possible because we have this excellent beam quality at MAMI, a beam which is narrow about 300 micrometer, and we controlled that simply by thermal cameras. You see, this is the situation when the beam really passes the lithium along 5 centimeter, and this is when the beam was off a little bit, and then you can tune the beam and improve your luminosity. We did 2 runs. The first run was about 2 weeks in 2023 with a natural lithium. That means we had not only lithium-7, which we wanted to have with 92%, but we had also some contamination in natural lithium-6. And since then the argument came up, what would be if this, what we see, the peak, is if this is due to the lithium-6, that means it's hydrogen-5. We made an additional run with an enriched lithium-7 target, and we observed the expected rate, the expected spectrum for this enriched target. And by the way, if the peak, I will show you in a second, would be due to hydrogen-5, that means to to lithium-6, this peak would be at 10 MeV excitation energy in hydrogen-5, which is far beyond the known ground state of hydrogen-5. So we are sure that we are having a reaction on lithium-6, on lithium-7. Oh, okay. And then the analysis is easy. It's very straightforward. It's the question of 1 hour. Of course, you have to do some calibration, energy calibration, momentum calibration. So it's more complicated. But in principle, it's very easy. You plot the coincidence times of these 3 particles. Usually we do this in a way that we plot on one axis the time between, that's here spectrometer A and B, that means between the proton and the electron, and the true 2 particle coincidences are shown here by the line. And on the other axis, you plot the time between the spectrometer A and C. That means it's the time between proton and pi plus. This is this coincidence. The real coincidence is 2 particle coincidences. And the coincidences between the electron and the pion appear here on the diagonal. And the real triple coincidences are here in the center of this spectrum. And then it's straightforward. You make a cut on the central part, and you calculate the background by these different areas. There's no other modeling or whatever needed. It's simply just calculating the background by the integrals in these different spectra with proper weight, of course, because you have to weight that to the area here. There's no fitting, nothing involved in to calculate the background. And that's the spectrum what we observe. This is what we think is the ground state of hydrogen-6 now. It has more than a 5 sigma significance. You see here in the bound region, this background here shown by the histogram is fully compatible with the number of events seen on the bound region. So there are no events in the bound region, no peak, no structure. On the right-hand side here, that means in the unbound region, there is some additional yield, obviously. So there could be some continuum, some excited states, but that is not statistically significant. We cannot make, with that statistics, we cannot say anything about that. The peak here has a resonance energy of 2.3 MeV with a statistical error bar which is dominating. The systematic error bar, we are still working on the final and even improved calibration of the spectrometers. Maybe this will go down, although I don't think so. And then we have the width, which is, of course, dominated by statistics with that peak. You see, even with something like 20 or more than 20 events, you have some uncertainty. The hydrogen-5 resonance, if that would be on the lithium-6 target, that's what I said, it would appear here. Yeah, but it would be a neutron which is very close in momentum space to the hydrogen-5. Yeah, so it's like in the case when you have beryllium-9 and a neutron and 2 alpha particles. Also the kinematics would be different. Also the production process could be different. But we see a peak with a width of 2 MeV, and so yes, I mean, if the neutron is there, but that would be even more unlikely, because then you should have additional background from all the other neutrons around. Particularly, we would expect some background here on the left-hand side in this case. Because it would be very unlikely that the neutron is just in the momentum region of the hydrogen-5. There would be many other neutrons around that. So, this is now what we observe. You see, this is our measured here, the star, and here you see these previous measurements which I mentioned as they are published. Whatever that means, of course, in these single events. Then you have here the recent measurements, 2024, which shows a signal here. And this is these older measurements which I showed with pions, which are above here. And then you have we compared it here to the different predictions. You see the most recent one from EMICO is up here down. So this doesn't simply fit the spectrum. Okay, I think I'm done, so I will not show you the outlook. Of course, we can use this method to look now for, maybe I show just what we have in mind. If I can come back, okay, this is the back button. You can use this scheme also for the trineutron, also the hydrogen-5, and you can, of course, use for more exotic ones, but there you need a pi plus reaction, and that cross-section is additionally lower. So for that, you would really need a factor of alpha, probably more, That means 100 more in luminosity. So this is in principle possible, but difficult. Okay, I will show here, leave you with the summary. I should mention those 4 people, those 4 students who mainly worked on this experiment. That is Tianhao Shao from the Fudan University, who analyzed the data, then Ryoko Kino and Kotaro Nishi from Japan, and then Pascal Clark from Mainz. So these are the 4 main students who did all the work. Thank you very much.
Thank you also for being on time. So we have 5 minutes.
Which is
for
unusual.
questions.
Normally I'm never in time. Huh?
So very good.
Okay, so I'm here.
Yes.
Okay. So, and one question is, in your the experiment, you use lithium-7 target, right?
Yeah.
So is it enriched or natural target?
Well, that's what I said. We had 2 runs. One was with the natural target, which is more than 90% lithium-7. Is it? Must be some, no, must be later. Oh, here. Here. So you had a run in 2023, in late 23, where we had about 2 weeks running with natural lithium, which is of course dominated by lithium-7. And then we had, in addition, because this question came up whether it could be due to the lithium-6 target, we did a run with an enriched target, which is purely lithium-7, and we saw within statistics the same bump.
Okay, so then I just maybe in the question is related to LIMAS, and then so that you in the observed data is very close to the hydrogen-5 experimental data. Then, and I just suspect that you would just observe the H5 or not.
No.
So then, and because our calculation following, and if we trust the hydrogen-5 experiment to the 2-bit resonance state, and energy is around the 2 MeV, above the triton plus 2 n threshold, and gamma is 2 MeV. Then hydrogen 5 and hydrogen 6 is rather higher, around the 7 MeV, and the decay width so rather broad. So in this way, our calculation is strongly dependent on the hydrogen 5 energy position. Then also, and Michel, you show up the Michel, who is it? Michel Lee. I forgot. So physical review see paper using the gamma shell calculation. Also, he just say hydrogen 5 is energy is around 1 MeV and decay width around less than 1 MeV, almost 500 keV, very shallow. And in this case, hydrogen 6 and together with hydrogen 7 is very narrow, and also an energy is lower. Then also my calculation almost similar. That means if the hydrogen 5 is like in narrower, then also our calculation of the hydrogen 7 is also a very low energy, and decay width is so narrow. Sometimes we have a bound state. So then and hydrogen 6 is indicated that the hydrogen 5 should be very lower energy, and the decay width is so smaller. So therefore, in order to confirm that, I would also suggest to you to measure the hydrogen 5 together with hydrogen 6 and hydrogen 7. That's my comment.
Well, first of all, you cannot, the energy scale, you have to be careful. If that would be, for example, hydrogen 5, what we observe, you have to analyze the event as if it would be a lithium-6 target, because this can come only from lithium-6 target. And that would move the peak to about 10 MeV. So this is, first of all, the experimental point. The other point is, yes, in principle, that's possible, because for that you only have to change to a lithium-6 target. And enrichment of lithium-6 is a little bit more complicated because it has only, 7% natural abundance. So, but that can be done. Lithium-6 is not so expensive.
Okay, so then I would suggest to measure the hydrogen 5 measurement, because also this is very important to measure hydrogen 6 lambda, right, from the hypernuclear physics. In any case, hydrogen 5 measurement is very important.
Yeah. I know, I did actually correct the transparency when I said here that hydrogen 5 is well established. I looked yesterday evening in the data and I said, well, yes, it looks nice, but it could also be more complicated, I must admit. No, the problem is the following: I do not know who will do the experiment. I'm not only an experimentalist, but I'm retired now. So this is the major difficulty. That.
Okay. Josef, thank you for this extremely stimulating talk. I was wondering about, just curiosity, so you have, you are able to identify triton plus 3 neutrons, but you could have deuteron.
No, we did not, it's a missing mass experiment. It's no identification.
But probably we are below the threshold. The energy that you are is below the breakup threshold of the triton, no? Because I was wondering.
No, in the experiment, it's a missing mass experiment. That means...
I know, it's in indirect.
Here.
Yes.
It's
I
a typical
understood.
missing mass experiment.
Yes.
No?
But you could scan, this was my curiosity, you could have a situation with a deuteron and 4 neutrons, proton and 5 neutrons. If you have seen, if you are able to see some strong correlation as well or not.
Well, this what you are talking about, they would appear here in the bound state region somehow. And you see that the background is really, there's no normalization in the background. Here it fits perfectly. Actually, I'm surprised how well this fits, because if you add up the numbers here and the background, they agree more or less. Much better than statistics, actually. But here there is some, you see there are more events above here than below the background, so there may be something like that. But
You can identify the threshold by the energy.
the NN, oh yeah, we could look at, I don't know, I don't have it in mind. You mean the threshold for tritium going into deuterium plus...
And then proton plus...
yeah, I don't know how high that is.
There is one data.
How much? 8 MeV, so it would be here around somewhere. Could be.
But is there any prediction for an excited state around 20 MeV or not? Because
not that I know. I mean, I showed this one experiment where they associated some additional bumps with excited state, but I don't think that there is a prediction for excited state at the moment.
This is really interesting. Can you go back to Emiko and collaborators' level diagram? So reading papers on exotic nuclei, I have learnt to think about the concept.
This one?
Well, actually, I think 2 forward.
2 forward, 1, 2.
Yeah, this one. So I've learned to think about the concept of sequential decay. So maybe I can restate Emiko's question as why you don't think, do you think that there is a contribution to your data from the sequential decay of hydrogen 6 into hydrogen 5 and a neutron?
Well, it would be a neutron extremely low in energy, no? Compared to the hydrogen 5. It would be a system where, so to say, a hydrogen 5 plus a neutron is flying together.
Yep.
And if that would happen,
Yep.
this is, yeah, exactly. If that would happen, it would also mean there must be much more neutrons, because you cannot just have neutrons flying in one direction. You will have a broad distribution of additional neutrons, and they would produce, in this missing mass experiment, an additional broadening of the whole situation. So this is, I think it is unlikely. I mean, one would have to do a phase-space calculation or what have you, I don't know, simulation, but I think it's a very unlikely process. Because suddenly you have only one neutron, and you know this neutron is always flying in the direction of the hydrogen 5, and this is unlikely in my mind. I did not say that my reaction mechanism, which I proposed, is correct. I said it's a complete...
It doesn't matter if this one particular is correct, but it requires that you kind of to convert proton into a neutron by emitting very energetic particle, and this neutron remains kind of very slow for your state to survive.
Yeah, but there are certainly then additional reactions going on in order to form this hydrogen 6. So it's unlikely that the remaining hydrogen 5 from the hydrogen 5, I think, from the lithium target, that you then additionally just put this neutron inside this or close to this target by this reaction, because this process is of course broadened by the whole Fermi distribution. I mean, the scheme which I showed is very naive, and of course you have all sorts of, where is it? Oh, it's not here. All sort of additional motion. I mean, here you have Fermi motion involved, here you have Fermi motion involved, so you have a broad phase space. And that is what we also see in the missing mass spectrum. We have a broad acceptance of the missing mass. We allow a lot of missing mass region, plus minus about 60 MeV. So we have no kinematic constraint on the missing mass.
Okay, so let's thank Josef again. I think it's time to go. And we move to the next speaker.